All right, it's 40 after, so let's go ahead and get started. Reading for this week, I'm going to finish up, do a little more on this static equilibrium. We started doing that last time, and I tried to introduce it with a spool to sort of get in your minds that when you're dealing with a static equilibrium problem, it really is a rotary motion problem in disguise. So we'll do a little bit more with the hinged beam architectural problem, and we'll do some other problems like that. And we'll think a little more about the body too. We'll think about our anatomy and how it is that static equilibrium also plays a role in terms of how our mechanics of bodies work. Oh yes, and so next week is spring break. Enjoy that. After the break, yeah, happy voices. All right, after the break, we're moving around to chapter 15. And we're going to come back to some intermediate chapters there, but we're going to do things in a different order than the book. We're going to go from static equilibrium, that's what we're doing today, to fluids. So just heads up, static equilibrium, right? Yeah, and we'll talk a little bit about what constitutes a stable equilibrium point versus an unstable one, something else we're going to talk about today. So last time, we looked at this demo over here, and the question we asked was, what's the tension in this chain? Remember that? And it turned out that in general, to solve this problem, right, you have to solve Newton's second law for the x direction, horizontal direction, as well as the vertical, right? And then separately solve the Newton's second law for rotations about some pivot point. And we found that if we chose the right pivot point, we could just do it with rotary motion, just the rotational version of Newton's second law. We didn't really have to have the x and y, either of the x or y, Newton's second law for the linear sort of case. But we could ask other questions too. In particular, what we did last time is we said if we chose this as our pivot point, remember that? Okay, well that means that the torque is going to be due to the forces from the hinge on the beam. We're going to be zero, right? There may be some horizontal component, there may be a vertical component, but neither one really played a role in terms of Newton's second law for rotations if this is our pivot point, because then the radial distance, right, from from the pivot point to where the force is acting, that's zero. So there's no torque from either of those horizontal or vertical components of the hinge force on the beam. So that made our problem easy because we didn't care about the forces from the hinge. All we wanted to know was the tension in the rope. But we could have also been asked, what are the hinges? Like, hinge forces? What is the force of the hinge on the beam? We could have been asked that. So how do we solve that problem? So let's think through that, and maybe I'll do that right. Maybe I'll do that on this board right here, and I'll work my way through it. So just to remind you, when I have a problem like this, I'm just dropping a little picture. I've got my tension. I actually forgot how I defined this thing last time. I'm just going to define phi down here. I forget how I did it last time. Here's my beam. Here's the center of mass of the beam. So once again, and here's the hinge, right? So here's my hinge. Now I like to label this thing as a hinge to remind me that it can be that this guy's free to rotate. But by hinge, I don't mean the pivot point necessarily. We have a choice about the pivot point. In fact, we also have choices about what object of the problem we're going to be thinking about for Newton's second law, right? So I just want to be clear. When I write hinge here, I don't necessarily mean pivot point. Okay, great. And this thing has some mass too. There's mass of the beam and there's mass of a weight hanging on the end of the beam. So one question. Let's see. The first question we asked last time was what was the tension. So let's figure that out. Let's remind ourselves what the tension was. Remember, we solved that. Let's just skip to the chase right now and solve it just by doing Newton's second law for rotations about the hinge to repeat that calculation. So before I do that, I'm going to go ahead and make a free body diagram. Looks like this, right? And as I mentioned last time, we've got a couple choices about how we represent the force from the hinge on the beam. We could write it as an angle. We don't know what the angle is yet. That's one thing we're going to find out in a few minutes. But what we can do right now is just define the components. I'll just go ahead and do that. And I mentioned some conventions last time. I'll state it a different way right now. Usually if I've got the x direction pointing that way and y direction that way, if I define these components so that they point in the positive x direction and positive y direction, then I don't have to worry about signs as much. The problem with that is if it turns out that, if in the beginning of the problem I know that the force, so we worked this out last time, but let's think about it. Okay, let's probably get a force to accept the hinge force and see what we can figure out with the hinge force. So I've got, first of all, a force to the tension, right? I've got a force to the gravity acting on the beam. And where does that act? Yeah, center mass of the beam, so it's right here. Now the thing is, lots of students refer, in office hours, I'm hearing lots of students referring to the force of this weight on the beam as gravity force acting on the weight, and that's not strictly speaking correct. So there is a force of gravity acting on this weight. It has magnitude m sub w for mass of weight times g, right? And that's the force of gravity acting on this weight. Well, by Newton's second law, the tension in this little rope right here, which is different maybe than the tension up here, right? That tension is equal and opposite to that one, and then by Newton's third law, the force that is exerted on this beam from this rope, right, is equal and opposite to the force that this rope is exerting down here. Actually, those Newton's third law, you need to have Newton's third law and Newton's. You have to go through a few steps of Newton's second and third laws. Ultimately, yes, it turns out the downward force acting on this part of the beam is the same magnitude as the force of gravity acting on this weight. But it's worth pointing out that this is not strictly speaking the force of gravity acting here, right? And so just keep that stuff straight. Gravity's acting effectively right here on the beam. This is really due to some tension of this little rope. But that's okay. We can go ahead and label it this way as long as we keep straight the masses and remember where it came from. There's one thing I want to remind myself to mention in the lecture, but it's not going to be for this. Well, let me say it this way. Suppose this were a rotary motion problem as opposed to a statics problem. And this thing is free to rotate right here. And we cut the rope. We cut the chain, right? So there's no tension here anymore. In that case, you can see what's going to happen, right? This thing is going to move. It's going to go up or down. Down. It's going to swing down like that. If I cut the chain, obviously the thing's going to fall, right? Suppose you have a problem like that and you want to calculate what alpha is, what the angular acceleration of this bar is. You can certainly have a problem like that in midterm. In fact, I just posted a bunch of old midterms. And don't look at them until you're ready to practice for the next midterm. But I put them up now just because spring break coming up gives you a little leeway about when you look at them. But when you decide to look at those, you'll see problems where things do stuff like that. And if you want to calculate what alpha is, you'd say, oh, I see, there's some downward force due to this little rope hanging down over here. Maybe I could, similarly, instead of having it hanging from the bottom, I could put it sitting on top. Either way. The thing is, what I'm getting at is that when this starts to move, right, at some point, if you wanted to ask what's going on when the bars move a little ways, you have to figure out exactly what alpha is at this stage. You'd have, or frankly, even if you don't know what alpha is at this beginning stage, you have to worry about what the moment of inertia is, what I is, right? But it depends on whether or not this mass is hanging from a rope or whether it's nailed on. That actually can change the answer. That's kind of a subtle point, right? Why is that? Well, it doesn't change the force, but it does change the moment of inertia. If you have a mass that's up here that's nailed on to this part of the beam, right? Then when this thing starts to rotate, that mass is rotating with the beam if it were nailed on, right? And that means it would give you a greater moment of inertia compared to one where it was free to slide. So this thing we're sitting up here and there's no friction on here. Then that weight effectively is going to fall without actually rotating with the beam. It's going to fall sort of straight down. It's a little complicated whether it's that exact here, it gets pushed off. Actually, it's going to go that way a little bit. But the main point is that it's not actually rotating with the beam. And if I got a weight hanging on a rope, that's kind of a subtle situation because as this starts to go down, well, initially this guy starts to follow a circular path, whereas he wants to go straight down under gravity. And then funny things happen, like a rope's going at an angle then, and then, well, the angle gets complicated. So exactly what physical situation you've got can change your answer, even if you're only concerned about the very first moment after this is cut. right away it starts to rotate. Before there's any chance for this weight to for it to matter whether it's going straight down or to the side or whether the rope's turning at an angle or whatever is happening. Right away there's an influence, not because of the direction of the force, but because of what you would calculate the moment of inertia to be for this beam rotating about this point. If the mass is nailed on, you have to add on, and if this length is L, right? If the beam is L long, you have to add on a term that goes like M sub W times L squared. That would be that contribution of the moment of inertia about this pivot point for the fact that there's mass is nailed on. But if it's hanging from a rope, you wouldn't do that. You'd say, well, he's actually not rotating, he's just going straight down initially. Anyway, so it's sort of a subtle point. I thought I'd bring that up. So if you have a problem with a teeter-totter and there's two kids on there, right, and the kids are really holding on tight, then they're moving with the teeter-totter, then you include their masses and their distance from the pivot point, wherever you decide that to be, when you figure out what the moment of inertia is. But if they're, if they're not holding on tight and they fall off the thing when it rotates or something, then they wouldn't be included in the moment of inertia. Anyway, all right, enough of that subtlety. So back to the problem at hand. We're not going to cut this thing. It's a statics problem. That means that we're relieved from having to figure out what the moment of inertia is because alpha is going to be 0. So when we write down Newton's second law of rotation, it's going to go away. All right, so we're back to our big diagram. What I got all the forces on this problem except for the hinge forces. We can tell which way, we did this last time, which way the horizontal component of the hinge force is going to be pushing to the right or the left on the bar. It's got to go to the right to counter the fact that the tension's going that way. Correct, yeah. So I'm going to go ahead and draw it that way. And I cleverly chose my positive x direction to agree with that so that there's no sign issues. I can say, oh, this is just force due to hinge in the x direction, and then I'll do the same thing for y. I don't have to be upward here in order for this thing not to be to fall that way. I know that it's going to have to be going up, and I'll just label that. I can give myself a lot of room here. That's force hinge in the y direction, and it agrees with my positive direction for y-axis. So I'm avoiding all my sign issues. Very good. Super. So then if I choose this as my pivot point for this problem, I say, okay, let's do, we're going to ask for tension initially, and later on we're going to be asked for what's the force on the hinge. That's what we're going to be asked, right? So first, for this part, we figure out last time, the quick way to do that, put the pivot point right here. So I'll say, okay, pivot point is at hinge. If I do that, I'd say, all right, that means that I've got, see, I'll call this angle phi, just like I do up here. Say, all right, I've got how many non-zero, see, I've got 3 non-zero torques, and I do my net torque, right? I've got tension. So again, if I define this as my positive direction for rotation, which I'm allowed to do, is tension giving me a positive or negative torque about this pivot point? Negative. So it's pulling that way. It's trying. If that was the only force acting on the beam, and that's my pivot point, it wants to rotate in a counterclockwise direction. So I know I need a negative. And what's it going to be? It's going to be this length. So what's that length? It's going to be the full length L from the pivot point all the way where that force acts, times the full size of the force, that's T, times the trigonometric factor to give me, well, what's going to be sine of the angle between this vector pointing that way and this guy. That's this angle. That's pi minus phi. But sine of pi minus phi is equal to sine of phi. Sort of the happy coincidences for me here, so I can get that wrong instead of gradient. There we go. Very good. So that's the torque of that guy. And then the other ones are much easier because the forces are just in the vertical direction. So that means the angle between that vector and that vector is 90 degrees. Same for that one and that one. Both of these guys are giving me positive or negative torque. Positive. Both these guys are trying to rotate it. That's right, with positive sense. Good. So I can just lump them together and say, all right, well, I'll do this in 2 steps. Make sure it's clear what I'm doing. L over 2 is that distance, and that force is mbg. So far it's all this review, but in a couple minutes, well, less than that, in 1 minute we'll be doing, we'll extend this calculation. And this is going to be the full length L, right, for this one, and it's mwg. So in fact, it makes sense, right? This mass over here has per kilogram. If you put a mass out here, it has a bigger effect, right, than putting a mass over here, because it's got a bigger radial arm. Right? So it makes sense. You get a factor in front of this guy that's a half as big as that one. It's further away from the pivot point. It has a bigger effect, more torque. Longer your wrench handle is, the more torque you get, right? Great. So we get all this stuff, and it equals what? It equals, sorry, not m, it's I times alpha, but alpha is 0 for statics problem. And it would be I not about the center of mass. It would have been I about this point. You have to worry about whether this guy's nailed on or dangling from a rope, but I don't have to worry about it statics problem. Okay, great. So good. So then this gives us our expression for t, and we can solve for t. What do we get? I can lump these together. So this is, I get an L times t times sine of phi on the bottom, and then on top I've got mb over 2 plus mw, all times L, because L is common, and G is common. I think that's correct. I sort of crammed it into this 2 here. Sorry about that. Make sure it's clear what I'm drawing here. So I think that expression is correct. Everyone agree with it? Oh, that's it. I have an extra t in here, don't I? I didn't need the t in there. How's that look? That looks pretty good. Super. Let's make sure I have the right units. So tension is a force. It should be in newtons. Is the length times meter per second squared. I need mass. I do. I have mass. Good. And this, oh, but I have length down here. What did I do wrong here? Did the length fall out? Oh, yes, of course it did. So I've got F equals ma, right? So we get a force. I need mass times, oh, very good. So that's the right units. Nice. So I think that's right. And it makes sense. It doesn't matter how long L is. It does matter how big the masses are. So notice that the tension gets bigger if I hang more mass on this thing. And that makes sense, right? In other words, I think, is this thing actually reading? Can you see what it says? No. See if I can turn that on. Although it's not going to shock you. I'm about to show you. See if I can turn it on. What'll shock you is if I can figure out how to turn it on. Oh. Too many knobs. I'm not going to be able to do it. I'm not going to be able to figure it out. No. You'll have to take my word for it. You'll have to take my word for it. But here's the point. The point is that if I push down right here on this weight, in other words, if I add more mass on, right, that is going to increase the tension up here. But that makes sense, right? If I push down right here, the tension should go up. Similarly, if I push right here, if I push down right here, that should also make this. In fact, if I push hard enough, it'll probably snap this thing, right? I'm not that strong, but if I were to jump on it or something, this thing would break. And that makes sense. So that's good. It makes sense that our answer for tension depends on these masses in the numerator. It's better, right? Otherwise, you make a mistake. It also depends on the angle phi. So the sine of phi is a function. So sine is a function that grows with growing phi, right? When you're between 0 and 90 degrees. And that makes sense. If you make phi get really close to 0, what does that mean? Well, that means that I'm having a very shallow angle, having a very horizontal sort of a rope. Remember we did that demo a few lectures ago where a couple students came out and lifted up some weight by pulling on a rope. The further out I made them stand so that the rope was more and more horizontal, the harder they had to pull, the more force they had to exert to lift the same amount of weight. The same thing's true here. If this thing is further and further like this, lower and lower angle, the greater tension you need in order to make this thing not fall. Makes sense, right? And you might say, wait a minute, if sine is getting smaller angle, yeah, but it's in the denominator. So tension's going like 1 over a function that gets smaller with phi. So that makes sense. Good. So I believe my answer, even though I was cranked out here. I had to think about it a little bit to get my units right and make sure I didn't have extra factors floating around. But yeah, it looks right. And of course, the bigger the strength of gravity is, the bigger the tension's going to be, right? If there's no gravity here, there'd be no tension in the rope at all. G goes to 0, T goes to 0. So this makes sense. So how about these other things we're interested in finding out? The forces acting on the hinge. So now we really do have to use, well, let's see, is that true? Could I get away with just doing it with Newton's second law for rotations? Well, we certainly need another equation of some type. This equation actually was judiciously chosen. Like we were smart about choosing our pivot point so that we could eliminate the forces due to the hinge, right? That was a good call because we wanted to calculate the tension and we wanted to do it in expedient fashion just with one equation. But now if we want to know the forces acting from the hinge on the bar, now we need an equation that explicitly includes them. So what if we included, what if we changed our pivot point? What if we wrote down Newton's second law for rotations about a different choice for the pivot point? So if we chose this one over here, what do we get from that? So let's see what we get. So if I try for my pivot point the far left, left of bar, all right? So what do we get then? Newton's second law for rotation. So what's interesting is that this will actually give us a different equation. So we're just applying Newton's second law for rotation, same general equation, but with a different pivot point. We get a totally different equation out of it, right? Because now what's going to be 0? Well, if this is our pivot point, we're not going to get any torque from tension. And we're not going to get any torque from the mass of the weight, or from the force of the mass of the weight is exerting on the bar, right? Yeah. Oh, I'm sorry, did I say left? I meant my left if I'm facing that way. Yes, it's your way. Right. I think you're correct. That is right. And if we're both facing that way, yes, very good. Yeah, keep me honest. Hard to do. Full-time job for you guys. All right, so we got right side of the bar. There's your pivot point. Now, some of you might be scandalized by that because that's not where the hinge is. And say, well, wait a minute, it doesn't actually rotate about that point. But that's okay. It's a static problem. It's a stationary point. We're allowed to do it. Even I didn't want to do it, so I put stuck left in, I guess. It's abhorrent to me for some reason. But that's okay. Totally legal. So we use the right bar. Use the second law for rotations. Well, the torque from tension is 0 about this pivot point. The torque from the mass of the weight over here, or not the mass of the weight, from the whatever it is, the tension of this rope holding up the mass of the weight, this is going to be 0. But now we do get a non-zero torque from the mass of the bar itself. The bar now, if you think of the bar as pivoting about this point, if you were to put a nail through it here and say this is the only mass acting on it, does that result in a positive or a negative torque? I'm hearing the right answer in the front from a couple people, but does everyone see what the sign of that torque is? So if I'm pulling down right here, and this is where my pivot point is, it actually results in a negative torque. Even though that's not what would happen by cutting this rope or anything else like that. It's sort of hard to think about it that way, but that's correct. So it's a negative torque, and its value is negative, so it's negative mb times g, that's the strength of the force, times the radial arm, which is sine of beta, beta is 90 degrees, sine 90 degrees is 1, times that distance is L over 2. So I get L over 2 times mbg, and it's negative. So that's the torque due to that guy. What about the torque due to the horizontal component of the hinge force? Yeah, so it's acting at a point that's L away from the pivot point, but notice it's pointing right at the hinge, right? It's horizontal force. Now, some students in office hours had saw some problems at the board with me coaching them, and one thing that came up was, well, how thick is the beam? Because if the hinge is at the top of the beam, say, and the beam's got some thickness, so then you get into an issue like, okay, there is a little bit of an angle. So for this problem, I'm going to make the approximation that the beam is very thin compared to its width. So I can ignore little tiny angles because maybe the hinge is at the top, the bottom, or wherever it is, and maybe the force over here is acting at the bottom instead of the top of the beam. So in this problem, we're not going to worry about that. We're essentially treating the beam like a one-dimensional object. It won't always be stated in a problem where in some cases it'll just say explicitly, oh, you can treat the beam like it's infinitely thin or something like that. But if it doesn't, it's natural to assume that in a problem like this, you have a long, thin beam, but you might state it. You might state your assumption and say, oh, I'm going to assume that the beam is very thin compared to its length. In that case, we can ignore the fact, or we don't even know exactly where that horizontal force is acting on the left side of the left, yeah, it is the left, right? The left side of this beam. And we have to know exactly where the pivot point is, the top of the bottom beam, doesn't matter. So in that case, yeah, it's exactly equal to 0, the torque from this force, because it's pointing straight at the hinge. So the only other surviving torque is going to be from the vertical force that the hinge exerts on the beam. Is that going to be a positive or negative torque about this pivot point? Yeah, here's people say positive. That's right. If I put a nail through this side of the beam, and then I only exert this vertical force from the force of the hinge over here, right, that would result in a positive acceleration, positive sense, right, for rotation of my beam. So yeah, it's positive torque. So I would write positive, what is it, at full length of L times mass of, what is, oh sorry, no, it's not mass, it's times the force of the hinge in the y direction. And as we mentioned before, if I didn't know at this stage in the problem whether the force of the hinge is pointing up or down, but I chose to draw it this way in my 3-by diagram, I would just treat it as if that's correct and then let it carry it through. And at the end of the problem, if I get a negative number for f sub hy, I'd say, oh, clearly it was actually a downward force, and I just draw it the other way in my diagram, and that's fine. It's going to turn out to be positive, though. Clearly it needs to have an upward force here, otherwise the beam would fall. Right? You can sort of figure that out. Great, so now we've got two opposing torques, and they're the only surviving torques. That one's 0, that's 0, that's 0. This has to equal I alpha. Oh yeah, this is I about the right-hand side, but it doesn't matter because alpha 0. So what does this tell us? Well, once again, the L's cancel out. See that? L's in front of both terms. And now we get an expression that tells us exactly what the y component of the hinge is. So just using a single application now of Newton's second law for rotations gives us part of what we wanted. We were asked for the full vector of the hinge force. This just told us about the vertical component, but that's nice. It actually, so we're halfway there, right? What is the answer? It's equal to positive mbg over 2. I didn't screw anything up. I think that's correct. Okay, so we're halfway there. Now to get the other one, well, it's interesting that if I want to get the horizontal component for the hinge force acting on the beam, there's no equation I can come up with Newton's second law for rotations for any pivot point inside the beam that's going to give me a non-zero torque for that force. Does everyone see that? Sorry? Repeat it. Yeah, I can repeat it. Let's see if I can repeat it. So if I choose any pivot point inside that beam, for whatever choice I make there, it's going to turn out that the torque due to the horizontal component of the hinge force on the beam, that torque has to be 0, because it'll point right at that pivot point. Now you could choose a pivot point that's off the beam, even though we're talking about the beam. You could do that. But rather than go there, what I'll do instead is use plain old vanilla Newton's second law, and I'll use that to figure out what the vertical component, because that's a valid law to use as well, right? And which one's be more useful for us? If we care about the vertical component of the hinge force, should I use Newton's second law in the x direction or the y direction? Everyone's saying x. I would use y, but because if I use y, then I can directly compare the did I say it backwards? I think I said it right. So if I care about f sub hy, right? If I write down Newton's second law in the x direction, then that has no contribution. So I won't get an equation that includes it, right? So but you can still solve it though the other way. If you let's do it for both. So if you have Newton's second law, let's see what the f